All right, all right. We are
All
live
right,
now.
we're
We're
here.
here.
Yes, sir.
What's up, Jose? How you doing, man?
I'm doing good. I'm feeling happy. A little bit
Feeling
scared
happy?
because we have some hard problems up ahead. But we're here to learn. We're here to understand everything, right? I think
Uh,
it's possible. But yeah. Other than that, I'm happy. I'm ready to go. How about you, Carlos?
I'm doing good, doing good. Uh, I guess I'm not so ready. Um, what time did you wake up?
I woke up like around 7.
Yeah. You wanna know
Yeah.
what time? You wanna know what time I woke up?
What time?
9:35.
Ooh, fast.
Was about 30 minutes ago.
Hey, all good though. All good. You got some extra sleep in.
Yeah. So little, not tired. I didn't wake up tired, thankfully, but I guess I just wanted to sleep in a little bit.
Yeah,
Um,
yeah.
but anyways, I made some coffee,
Okay,
and
okay, I see you.
but I just found out that I was given this coffee from my mom,
Mm-hmm.
right? And
Yeah.
there's three different coffee little bags of ground coffee. And
Uh-huh.
I was like, you know what? Maybe just try a different one, right? I've been doing it's called like Houston blend or something.
Mm-hmm.
And I decided to look if there's an expiration date. And turns out that all of the coffees that I've been drinking, they've been expired for more than 2 years,
Oh, damn.
including this one that I'm drinking right now.
Damn, brother. That's worrisome, bro. I mean, damn, bro.
And I should have
That's
known. I should have known because every time I go to my parents' house and look in their pantry for something that I need, it's always expired. Always.
nah, dude. Nah, bro.
So
But I
I
mean,
should
I
have
mean, you're
never
good
taken it.
though. Nah, but you're good though. You've drank it before. You'll be fine. You won't die. Some like
Yeah.
some stomach. It's a stomach. I forgot what the name is, but you might get like a stomach infection, but you'll be fine. You'll be fine.
Yeah.
You'll be
So
fine.
anyway, I just thought it was
But
funny.
nah,
That
nah.
I've been like, oh, this coffee's so good. Like, oh, I
Maybe
love
it's
it.
because it was fermented already. Like it's expired, so it gets that extra flavor.
I
It's like a
hope not.
wine. It's like the
But
wine where like the more time you leave it like being like fermented or something like that,
uh-huh.
or whatever the process, it tastes better. What if the same thing happens to coffee? The more you leave it, the better it tastes.
I guess.
Never
I
know.
guess. But yeah, anyways, that's just found out literally 10 minutes ago. And also it wasn't it's kind of similar to what I experienced yesterday, how I told you about the steak I was going to make.
Yeah,
I
yep, yeah,
I went to go play basketball. I thawed out my steak, right? Like before I left, I put it in a bowl of water. And mind
yeah,
you, it's in a plastic bag. Like it was frozen. So I
yeah.
put it it's in a Ziploc bag. I put it in the bowl. And then I come home and I'm like, oh yeah, like I got my potatoes and stuff. I went to HB get some potatoes, and then I was like, oh, let me just take it out the water right now. And I looked at it,
And
and
bam.
the bag was filled with water, and the steak was just floating. And I was like, there's no way. And then I pick it up, and you see the hole right in the middle of the bag, and it's just
Jeez.
like leaking its water or whatever you want to call it. And I was like, there's no way. So I was already like, you know what, I'm not gonna eat it. It wasn't until an hour later when I realized I didn't thaw out anything else because everything else I have is frozen. So I need to take
Uh-huh.
it out. So I was like, well, I guess I gotta eat it then because there's nothing else. Like, there's no more time for me to thaw out another steak or a salmon or whatever, right?
Hmm.
So um, I patted it dry. I made sure that There was no more water at as much as I can, and bro, it came out the best I ever made it. But
Really?
the
Damn.
problem is that I think that if there's still water, so it kind of makes me get a little like, um, how do I say, like, when I eat it, I'm thinking of it how it looked like with the
Oh,
water.
okay, I get you. Yeah, yeah, yeah.
So although it tasted really good, my mind was telling me like it's water, like it's a water steak.
It's a water steak.
Yeah. But
Damn,
anyways, other
bro.
than that's happened yesterday, and then today right now. So, anyways, what about you, Jose? How you doing? How you doing?
I'm doing good, pretty good. Yesterday made some tacos. I tried some new flour tortillas in the HB.
New flour
Uh,
tortillas.
yeah, they're like the ones that make there, like handmade. Bro, they're really good, bro. You
Wait,
should
wait,
get
wait,
them.
wait, 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 wait. You've never that wasn't your main tortilla that you would get?
No, I would get the ones that are already they're raw, because this one's already like cooked, semi-cooked.
I see what you're
I'll get
saying.
the
You'll get
raw
the ones that are
ones.
a little bit doughy, the
Yeah,
dough.
exactly. And I'll make those. Yeah,
Ah,
yeah, yeah, yeah.
okay.
And then but then my mom said like, no, if you don't wanna like put them that much, like, well, if you don't wanna wait for them to cook fully or that much, just get these, and they're really good too. But they're a little bit expensive, not lie.
Talking about the HEB
They're
ones,
yeah,
dude. That's what I grew up with right there. Those HEB
really,
tortillas. Yeah, they're really good.
yeah. Oh, they're really good,
But be
bro. And
careful. There's some that look the same, but they're butter. It's
yeah,
called,
yes, yes, yes,
and those are
yeah.
alright. But I grew up with the normal ones,
The regular
so
ones,
I
yeah.
can't
Well,
have no butter stuff. Unless I put in
I
butter
mean,
myself.
yeah,
Unless
that's
like
it.
I
I was
put
gonna
butter
say
myself.
that. I put some butter. I made one. I put some butter, and it was really good.
Yeah,
And my mom told me like the butter ones are good too, but I couldn't find them, so I just got the
yeah,
regular ones.
they're good. It's
But
just
they're
I
yeah,
can't like eat them. I enjoy the original ones better. Is what I'm saying.
yeah, yeah. I get you. I get you. And so I tried them yesterday. They were really good. I made some beans with cheese, white cheese, not yellow cheese,
Beans and
yellow cheese.
cheese.
Yellow cheese? No American cheese.
No American cheese.
I'm a hate. I'm gonna be a hater a little bit. I'm make something, say something controversial that might
Oh,
make people mad. But like
excuse me.
Tex-Mex, bro, Tex-Mex food, you know, not the best, not the best.
Tex-Mex is not the best.
Yeah, enchiladas. I
Yeah,
don't know
yeah,
if you
yeah.
got, yeah. Do you put like do you get like some yellow cheese
Uh,
or is it white cheese?
I don't want to call out my mom like that, but yeah, I
Oh,
use
she
yellow
put.
cheese.
Oh no, brother, no,
Dude, I'm
no.
sorry. I'm sorry I have to tell you right now.
We can't be friends, bro. End the stream right now. No, I'm kidding. But
Yeah,
yeah,
she does do yellow
like
cheese.
yeah, but like the yellow cheese with like beans and stuff, it's not really like it doesn't. It's not a really good mesh to
Uh-huh.
my liking. I grew up more with like more with white cheese and
With
all that
white
stuff.
cheese.
No.
I should tell her try a white with white cheese cuz that sounds
Yeah,
good. That sounds really good.
yeah, but it's a specific. Let me see. I think it's yeah, I think it's not the mozzarella one. It's like it's
The one that breaks up real easy like it's
yeah, yeah, it's like it crumbles. That's a good
and it's
one.
also it's
That's
a maybe a little bit there's more liquid and it's like a little juicy a little bit,
yeah,
right?
yeah, yeah.
That one?
Yes, yes, yes. Yeah, you can
I don't know
drain the
if juicy.
juice,
Yeah, I don't
right?
know if juicy is the right word to say, but like it's a little bit
Yeah,
squishy
it's
or like
I forgot the name of the liquid, but it's just like the liquid the cheese has,
yeah,
so you can drain it and you get the cheese.
yeah.
But like the white, yeah, I grew up with like the white cheese and stuff with
Uh
the
huh.
enchiladas. And so yesterday I was thinking I was making some beans, and then I was like, I put some white cheese, and I was like, damn, bro, why do people put American cheese, yellow cheese?
Yeah.
White cheese is the best to go. And I made some chicken, and boom, boom, boom. And so I made some tacos with beans, cheese, and chicken. They were really good. And but yeah, other than that, I'm ready to go, right?
All right.
Ready to.
glad
get
we
head
got our
into
little
this
yap
test.
session out the way.
Yes, yes,
And
yeah.
all right, let's get it, man.
Yeah, let's
So
go.
we got a couple problems today. We got this medium problem: construct binary tree from pre-order and in order. I don't know if we attempted to do this one already.
Yes. No, we were going to last stream, but we decided to do other ones.
Okay. Last stream we
Yeah,
ended
yeah.
up doing the manipulation, and that was because we had an exam last Wednesday, and to save our mental capacity, we didn't want to do these because our exam was later in the day.
Yeah.
So we didn't want to, or at least I didn't want to be all mentally drained by doing these three problems. And then by the time the exam comes, I'm toast. I already used all my mental capacity and stuff. Like, just trying to solve these damn problems. If
Yep,
that
yep.
makes any sense. So we did these easy problems. They weren't bad. Um, so yeah, we don't got no exam today. So back to our normal schedule. Just going down the line of the LeetCode line 75. So let's
Orcus,
see.
welcome to the stream, my guy. How's life going? It's going good, brother. Can't complain. Just trying to survive each day. How about
Trying
you,
to
my
get,
guy?
just trying to get this semester over with, man.
Yes,
Trooping, we're
sir.
trooping.
Slowly but
But
surely.
all right, we got the problem. We got the problem up, and
All right.
you want to read it?
Yeah, I'll read it again. I
All
got
right.
you. So this problem 1 of 5, construct binary tree with from pre-order and in-order traversal, and it says the following. Given two integers, arrays pre-order and in-order, where pre-order is the pre-order traversal of the binary tree and in-order is the in-order traversal of the same tree, construct and return the binary tree. Example 1, we're given the tree 3, 9, 20, 15, 7 with a pre-order of 3, 9, 20, 15, 7, in-order of 9, 3, 15, 27, output 3, 9, 20, no, 15, 7. Example 2, we're given a pre-order of -1, an order of -1, output -1. Yes, yes, yes. Alright, I think I have to. Yeah. I think for this one, we attempted it, I remember one time.
Yeah, that's what I'm
Yeah,
thinking. We had the
yeah.
Excalibur, right?
Yes. No, wait. No, start session, copy link. I'm gonna send
Orcus,
you
how you doing,
over.
man? How you
I'm
doing?
gonna
What's
send
been
you
up? What's been
the.
new? What's a recent challenge you've been going through? I want to know.
Alright, I sent you the Kelly draw. Yes, you can see. Yes, yes, yes.
Here.
I'm not sure.
See you. I see you.
There you go. I'm here. I'm here. I'm here. This is not the one. Uh, let me see.
Put that there. Yep, yep.
You got it?
Nope.
No. Oh, okay. I thought. Let me see.
Did you need me to?
No. I got you. I got you. I got you. There you go.
Okay. Okay. We're good. We're good.
We're good. We're good. We're good.
All right.
Yep.
So.
Okay. So.
We want to create a normal binary tree using a pre-order and in order. Using the pre-order version and the in order version.
Mm-hmm.
And
So.
the normal rules for a binary tree are or binary tree, is it? I get. You know what I get confused?
Yeah.
Binary search tree and a binary tree. You know what the difference, or if there's a difference of those? I know the
Binary.
binary search tree is like literally the left is gonna be less than the parent node, the right's gonna be greater than the parent node,
Yeah,
and so on
that's
and so
pretty
on.
much.
But the
That's
normal
pretty
binary
much.
tree, I swear I see some that like for example nine is greater than 3,
Uh huh.
so that's what I'm trying to figure out. Uh,
Binary trees means that a node has two. That's what's called bi, because it's two. Every node has two children, so it's a binary tree.
mm.
It's just like you can. It has no rules, no anything. Just that it has every node has two children. Binary search tree. It has bi, it has two children, but like you said, if it's the rule where the left has to be less than the node, then the parent node, and the right has to be greater than the parent node.
So what you're saying is if
I wrote
this
them down over here,
okay, but if this
but I guess,
was the
huh?
array, if this was the hold on, is this array the same as this um binary tree right here?
Well, it depends,
Like
because
how
if
do
this
you
is,
like from an array to drawing out the tree, how would that look like? Is it the parent node and the two children and then parent node, two children, or like
well, if it's a complete binary tree, right? That's the thing. If it's a complete binary tree, meaning like this one has other two nodes in here, right? Um, you get the parent node, the index,
Mhm.
and you get this one. I think it's two times. I'm not sure if it's one or zero. No, I think it's times something. There's like two formulas where you can get like the three, right? The three will correspond to this. The nine will correspond to 15, right? And the 20 will correspond to like the other following children.
uh-huh.
That's like if it's complete. Here, since it's not complete, we can't really use that. So
But what I'm saying is mine like ignoring this drawing,
yeah.
ignoring that you know it's not complete. How would you turn an array of nodes into a
Well, okay.
normal
So
binary
there's
tree?
there's a formula. There's two formulas
Two formulas.
that worked. Yeah, but I forgot them. It's two, 1, 2, 0, 1. Yeah, 2 times 1, right?
Huh?
And 2, I forgot. Let me search them up.
All right, no problem.
Array to binary tree for. Yes, I know it has to do with the 2.
What's up with
Uh,
this happy music, man?
um, I remember them. Okay, yes. So there's two formulas. 2 times I,
Two times I.
there you go. 2 times I, where I is the index of the parent, plus 1, and 2 times I plus 2. For example, if I have 0 here, 2 times 0, 0 plus 1 will give me this one. So this is the left children. Left, this is the right children, right? Then 2, 0, 2 times 0, 2, 0 plus 2, that's 2, 1, 2. So this is the right children. So this would be like 3. This is going to be something like 3, 9, 20, right? Bam,
Mm-hmm.
bam, bam. Then you go to the other parent, which is in this case 9, right? 9. Now the index is 1. 2 times 1 is 1 plus 1 is 2. So I have to go
Wait,
0,
two
1.
times one is two.
Oh, yeah. 2 times 1 is 2 plus 1, 3, right? So let's go
Mm-hmm.
0, 1, 2, 3. So now 15 is your left. Now 2 times 1 is 2 plus 2 is 4, which is 7. And that's how you get your binary tree. Then you check 20, but that's you check if it's out of bounds. If it's out of bounds, this one has no children. That's how you turn an array of nodes into a binary tree. If it's complete for sure.
So
And it goes
for
and it
for
uh-huh.
this right here, it would have actually the array would have actually looked like um no no
Yeah. Yeah.
something like that.
Yeah.
Okay. 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 Appreciate that.
Yes. Of course, of course. Yeah. No worries,
Uh,
no worries.
is it cool if I erase it now?
Yeah, 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 you do
Alright.
you. Yeah, for sure, for sure.
All right. So I needed to clarify that for me.
Ah, good, ah,
We're
good.
good. We're good. Going back to this.
Yeah. So I was thinking, right?
Okay.
Hmm. Hmm. Let's think about it. Let's think about it. What if, right?
Okay.
We know for sure that 3 here maps to this 3 over here. Yeah or nay?
Mm,
It's the same 3, same node. It's just like it's. I'm just saying like they're equal to each other. It's the same node,
yay.
pretty much. It's the same node. It's the same node.
That's a
Yeah.
yay. Yeah, that's a
Yeah.
yay.
Okay.
Uh huh.
Okay. Looking at this binary tree, we can see that all the numbers to the left are to the left of 3, right? All numbers to the right are to the right of 3, right?
Yep.
What if, let's say, we say, okay, fair. Let's go to this 3. Let's go to the left. Will equal the left children of 3, right? Will equal to the substring, right, of in order, the in order of 0 all the way to wherever 3 is. And I'm put this in parentheses to indicate uh like an index, right? For example, in this case, the left child would be right here in that section, right? In that section, right? Would be between 0 and 3, right? Or or 3 minus 1 per se, right? So it can be like just this number right there. Yay or nay? We can agree with that. Like the left children or the left subtree of 3, it's going to come from 0 all the way to the 3, meaning to the left of 3, to whatever numbers there is to the left, from 0 all the way to 3. Yay or nay?
Yay. Yay.
Yay? Yay? Okay, 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 okay. Now, with the same logic, right, we can say the right children is going to come from 3 all the way to n, where n is the length of in order. Yay or nay? It's gonna come from here.
That is
One
true.
of these nodes
It's
is
gonna be
going
the
to
right
be
child.
the right child,
You
right?
are the right child.
I am right
Three
child.
three is gonna be the father of one of those nodes.
One of those nodes,
You
yes.
seen
It's the
that? You seen
parent.
that show where it's like you are not the
Oh
father, you are
yes.
the father.
Uh-huh.
Yeah,
Yeah.
they. It's something like that where it's like you're the father of one of these nodes, or
Exactly, bro.
mother, or
Yeah.
mother,
Oh mother.
mother,
Never
or
know.
mother.
You never know.
You are the
Um
mother of one of those child. Okay.
is there been an episode where they say, "Oh, you're the mother," or is it always the father?
Jose, Jose.
No, no, no,
The
no, no, no.
mom is gonna know who their child is because they
I
birthed the
mean,
child.
yeah, but like, ooh, that is true. Oh my god.
We need to clip
My
that.
bad.
Can we clip that?
No, 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 no,
Can
no,
someone
no,
clip
no,
that?
no, no, no. Yo, yo,
Yeah, write that down in the
yo.
timestamp, bro. Write that down in the timestamp.
I didn't pull up.
There's no way. He said, "Has there ever been an episode that it was the mother instead of the father? Or you are not the father." But how would that work if the mom is the one that's having the child? That's just crazy. Good stuff, Jose. I'm proud of you.
I'm gone, brother. Bye, bye, brother. Hey, it's like one of those moments where you don't think it through.
Yeah,
You
you
just
don't think
say
it
it,
through. You just say it.
like,
You
oh,
just
it's
say
a,
it.
yeah, because I said like the father. Why not the mother? I did.
Yeah, yeah,
Okay, but
yeah.
yeah, yeah.
It's all good, man. It happens.
Like it happens. It happens.
Okay.
No, I'm good though. I'm
All
good.
right, we're
So,
here. We're here.
this is the father, right?
Yep.
Now I was thinking to do this a recursive way,
Horse.
right? Where the root is gonna equal to pre-order of 0. Yay or nay?
The root is gonna equal yes. Yes.
Yes. Yes.
Are you sure we haven't done this problem before?
We've worked on it, but we haven't solved it.
Okay. Okay.
So this will equal to 3, right? This will equal to the substring from 9. This will equal substring of 15, 20,
20 and 7.
and 7. Yes. Right.
Because this one goes it's from the left all the way to the first pre-order, the pre-order at 0.
Yes.
And
Yes.
if it
Yes.
was pre-order at 1, it's gonna go from 0 all the way to the pre-order at 1, which is 9. So the left all the way to 9, which it turns out 9's go all the way to the left already. So it's just gonna be there's gonna be nothing to the left of 9. Same for this one. Whatever number pre-order at 1 is, for example, it's 9. You're gonna start from 9 all the way to n, and that's gonna be one of the nodes. There is gonna be that's something we will have to check, because in this case 9 doesn't have a right child.
Exactly. So
I'm gonna let you keep going.
Okay. Let's see. So if we know 9, we know for sure where you made a good point, and I'm still trying to figure it out how. I don't have the answer with me, but right now it occurred to me, like if we go to 9, right? We can disregard all of this. We can forget about all of that and just pass in 9. For the 9.
And what's your logic behind that?
Because like you said, 9 has no children, 9 has nothing, right? And we for sure know that 9, right, would have children, right? If we had numbers, if 9 was like 9 and we got a number here, and we got a number here, and then we got 3. Now we can send this to the left, right?
So what's gonna be the condition that you know that 9 has no children?
Well, we don't know. That's the thing.
I think there is. It's gonna be if you're gonna store like 3 as a past node that we used, and if the next node right next to the current node you're on, for example, we're on 9, right? If the next node to it, to the right side, if it's a node we already went through, then that means there's no more children.
No more, yeah. Or what
That's
if,
what I would say.
right? Yeah, but what if, since we're like we're eliminating elements from the array, why don't we just check, hey, you're at 9, right? We sent 9, so now this is 9 over here. This is 9, right? This is 0, right? This is 0, because there's nothing. It's an empty list, right? Boom, 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 boom. It's an empty list, and we're gonna send pre-order of 27 of all of this, right? But since this is an empty list, that means that we finished with left. We finished with our left. Wait.
Yes.
Wait. Give me a sec.
The left makes sense. Like if there's nothing, then there's nothing.
Yeah, there's nothing.
The
On the right,
is
how?
where...
Well, that's the thing. We're gonna split the array in two. We're gonna send 9 one way and the rest of the other way. Right? We're not sending the entire array. We're just like saying, hey, just send 9, and do whatever you want with 9. Right? And over here we send 15, 20, and 7, do whatever with 15, 20, and 7. Right?
Okay. So that was the first. This is the first call. This is the
Yes.
first. Now the second one is gonna be pre-order.
So
0,
yes, okay.
Which would be
9.
And then
Yeah.
there's nothing to the left, so it'd be 0. And to the right of it, it would be nothing either.
Exactly. So we just return.
So you just
9.
put 9.
Mm-hmm.
And then this one, when does this one come into play?
Well, the first call of 3. So we go again on 15, right? We get 20 now, right? And we say, hey, 20, right? Let's go to 20 right here, right? And same process. We send 15 to the left, 7 to the right, and we go to 9, where we create a node of 15. We go, hey, 15, you got something to the left or right? No, return.
No, it doesn't.
Return, set the 20 left to 15.
Left 15.
And then 7 is gonna go there.
Yeah.
And be like, hey, you have left something right? No. Let's go back.
I think you got it.
Think so. We just have to
one. Now I want to give some
implement
input.
Yeah.
I like where you're going with it, but here's what I thought, and tell me if maybe there's some gaps that I missed.
Yeah, for sure. Go for it.
So I'm gonna do this with the laser. I don't want to mess up any of your drawings.
Yeah, go for it. No matter.
So
this is not complete. You know, I think there's still work to be done, but this is like the major idea.
Okay. What I was thinking, and here, just an idea. I want to go with your route, but you give me your opinions on this. You're starting off. We understand that the pre is kind of like our template on how we want to go by. Like we know that 3 is gonna be the top node.
Yeah.
We know that 9 is gonna be a parent of something. 20 is gonna be a parent of something. You know, but we want to use the in order to figure out which nodes are on the left and which nodes are on the right. Okay, so we know we know these two tasks, or we know what we want to do with these two.
Mm-hmm.
So it's very similar to what you were saying, is that we start off with 3. Okay, we go to 3 in the in order, and we get whatever's on the left, whatever's on the right. Okay.
Yeah.
The problem is that when you go on the right, you got to figure out which one is going to be the correct right child of 3, right?
Yes. Yeah, because we don't know yet. Well, that's the thing. We already know which one is child based on this, right? Because this is on pre-order. So you go 3, 9, 20, 15, 7, right? So we know for sure 20 is going to be the next route that we're gonna point to, which is over here, right? And we can say by this that we can do some like let me see, because I know where you're going. Let me finish. I'm gonna let you finish because I interrupted you. Sorry.
Oh, okay, you're cool. That actually got me thinking, and it made sense earlier, but it was something along the lines of, if we're at 3 and this node right here is next to 3 in the pre-order, that's a child. Okay. Then on the right side, if the next node isn't the one next to it, then see, now that's where I get lost. But Yeah, I lost it. Ignore it. Ignore it. Ignore it.
What do you mean?
No, I ignore it. I don't know. It made sense earlier in my head. I had this whole thing, and I did the iteration, and it worked, but I lost it. I don't know where it's at anymore. Yeah,
Because you're going based on like this to know who
I
is the
think I
next
was.
one.
I was trying to remember. Uh, I was trying to remember, but I think I
Yeah.
forgot it.
The thing with that is that 9, we're always gonna be the root, the right index, the right element to it is always gonna be the left, right? But when it comes to the right, you don't know where the right is. So that's it's gonna be a little bit tricky because it can be the 9, it could be 20, it could be 15, it could be 7, right? So that's where it makes it a little bit difficult. Where it's like, hey, where where do I go, or like where do I find the right? Because it all depends on how many nodes there is on 9, like in the all this subtree over here, and then we're gonna get the right. Same thing for here. We got 3. We know for sure.
I think I got it.
Okay, go for it.
Okay, so you start off with 3 because 3's first over here. You're gonna look at the left, right? And you're gonna say, "Damn." Okay, yes. Okay, ignore it. Okay, restart. You start off with 3. Boom, you found 3. Perfect. You put that in a as a node. Then you iterate. Now you're at 9. You go to 9, and you're like, all right. You want to find out what the left and right of 9 is. So you look to the left. There's nothing. You look to the right, and this node we already went through. Let's say we store it. We store that we passed through 3, right? So then you know that there's no children for this. Now you go to 20. You're at 20, you find 20 over here, and then you're like, okay, let me look to the left, let me look to the right. And you look to the left and you find 15. And 15 is not something we went through. So you put 15 as a child, as the left child. And then you look to the right, and then you see that 7 is something we haven't gone through. So then you put it as the right child. Then you're over here to 15. You go to 15, and you look at the left. You realize we already went through 3. And then you look to the right. You realize we already went through 20, so there's nothing. Then you go to 7. You're at 7. You look to the left. We already went through 20. You look to the right. There's nothing. So there's no children for 7.
So when you say children left for 15, is that for like 20, right? 15, the children to the left of 20.
Explain that
Like
again.
like 15 is gonna say be the children for 20.
Yeah, well, that's only if you're at once you're at 20, you check the left side, and you check the right side. And if the
Okay.
left node hasn't been checked, like if because each node we go through, like if I'm at 9, I store it. I store that I checked 9. If I went to 3, I checked 3, right? So if you're at 20 and you look to the left and this node hasn't been stored, then that means that's a left child of 20. And then you check the right.
Okay.
If 7 hasn't been stored up here, then that means it's a right child. And once you consider these left and right children, you store it as well. You just store the node or whatever.
Okay. Yeah. But how are you
So
gonna connect them to 3?
I didn't get that far. I didn't get that far. One
Because
step at a time. One step at a time.
it does make sense, like to store them to know, but
Yeah.
also, let's say we got 9 has extra nodes in here. Like 9 is a big subtree, right?
Mm-hmm.
How are you gonna know which one is which? Like you store all the nodes, all the left and the rights of each node. How are you gonna know?
Wait, yeah, you can connect it. I think if maybe not. No, 3. You go to 20. Hmm.
And like,
I
okay,
think there
let's
is a
say,
way, but I don't have that right now.
no, I get you. I think there's also a way, but I feel like it's gonna be a little bit hard because like I said, trying to find the right child. Because 9 is the left child, we know for a fact, right? But once we have a bunch of, like, let's say 9 is a big subtree, 9 is gonna have a bunch of numbers in between 9 and 20,
Yeah.
right? And you're gonna have a bunch of like nodes with all the left and the right children stored. And now you're gonna say, well, where's my left? What's my right? And the right, it's not 20. Well, in this case, it's 20. But let's say 9 has a bunch of elements. It's not gonna be this element right here. It's gonna be 20. So,
I'm not grabbing that.
because like let's say we have 9, right? We got. Let me put this a little bit large. Let's say. I'll put it right here. Let's say we got 3, 9, and then we got a couple numbers, and then 20, then 20, 15. I'll move it right now. I'll move it right now. No worries. 20 and 15, right? And you said, all right, let's store all these numbers to make it even a little bit even. You're gonna store all these numbers, right?
This is a pre-order.
This is a pre-order. Yes, we're
Okay.
gonna store these numbers. You are right. We're gonna go to the in order. We're gonna figure out which one is which. Yes. But so you're gonna go to 9. You're gonna get 7 and 23. You're gonna 20. You go 5 and 7, right? We know for sure 9 and its children is to the right. It's to the left, right? But let's say 7 had another, right? Another ones. So now we got 3, 9, 3 with the left children of 9 that have 7 and 23, right? And then 7 is going to have 23, 23, 57, 23, 53, and then 27. So you're going to store all of these children with all of the left and right. Yes, 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 all that stuff. But yet again, how are you going to determine which one is the left, which one is the right?
Well, I think it's just you're doing one left child and one right child at a time. You're not necessarily grabbing all the right, all the left. But
Yeah.
I would need to see the in order version of it to truly get what you're saying. Because yeah, we have the pre-order, but I would need an in order, and then
Well,
I'll
that's the
show
thing,
you.
because well, we can do the in order if you're willing to,
Yeah,
discuss about. Yeah, yeah,
I wanna see.
yeah, because
I'm gonna delete this part.
so we got this, we got we got 9, right? If I'm not mistaken. So let's remove 9.
And you also got duplicate numbers.
Yeah, that doesn't matter. I don't think that matters.
Okay.
Yeah, for right now, let's forget about the rule. Let's just say it's a binary tree. You're right.
Well, I need it to be accurate, Jose.
Come on, brother.
Where you're trying to find a counter example, you need to be accurate.
Fair.
That is fair.
9, 20, 9, 15.
How do you do that in order?
Pretty much since that's a pre-order, you go node, and then you go left node right, left node right.
Left node right, left.
So this is 15. That's 7. Boom. So now we go with our 3, which is in here, which are our left, right? So it's gonna go all the way to the left. Give me a second. Let me think this through. Right. So we go 3, and then we go. We go 23, 7, 7, 53. All right, 53. And then that's a left child. Then 9, 9, and then we got. Then we say let's go. We say we have 33. This one is 33 here. No. 33. I think that works. I'm not sure. But I feel like that's the accurate representation.
Okay.
Yeah, let's see.
So
So we go 3,
you're saying
9,
that if we go to 3
7,
and we're here,
23. Yeah.
the left is not 9 and the right's not 7.
Yeah, my thing is that you're gonna be able to get all the numbers, the left and right, but how are you gonna connect them? How are you gonna connect them based on like which one is left, which one is right? Because I'm based on what you're saying, right? Maybe there is a way, but like for right now, what you told me said like, all right, I go to 7, go to
Mhm.
left and go to right, 53, right? So it's 7 with children of left, children of right. We go to 9, right? Here at 9, we go to left, right? That's 53. We go to 33, that's 33. But are we going to consider 53 as checked, or we're going to just consider 7 as checked, or all three? Because all of this is a node.
I'm not seeing it anymore. I'm trying to do like the same thing that I was doing over here.
Well, it's because over here, right? You said, right, let's go to 3.
3.
We go to 3 over
Go
here,
to 3.
right?
Yep.
We go to the left of 9, right? Or we go, I thought I had the laser on. Sorry. So we go to 3, right? Go to 3, and then we go to the left of 9. And then you said 9 is not checked, or we haven't visited 9. So we say 9 is a left child of 3, right? Then we go to 9, check 9. We go over here. That's nothing. 3 is nothing, right? Since we already checked 3. So 9 has no children. Go to 20, 20 here, right? We go to left and right. Check if these two have been not checked. Well, yeah, checked 15 and 7, right? And then we set this 20 as 15 and 7. Like 20 with 15 and 7. Yeah or nay?
Yeah.
Yeah? Okay.
But you're saying how would you connect 3 to 20? Is what you're saying? Because we're
Yes.
getting the
Yes.
individual nodes, and we're
And
understanding that.
I think you can do it now that I think about it. Yeah, because we're doing 3, right? And you go to 9, so you check 9. 20, you just connect 3 to the next following, the next 20, right? But the thing is that what if 9, there's more numbers in 9, more nodes in 9, right? Like 9, I don't know, 10, 15, 10, 10, 11, 12, right? Let's say 9 had a children of 2 children, right? 9 will have a left and right. And then we go to the left children of 9, right? How? It's because I don't know. My dilemma. I mean, I'm pretty sure it works, but the thing is, like, how do we determine which one is the left, which is the right? That's my only thing. Because I
Like
think
when you're
let's do
when
this.
you're at 9 and you got a node right here, and you're saying how do you know if it's left or right, or what do you can you draw it out?
Yeah, no. Let's see this. I think I got the example now in my
Okay.
head. Okay, yes, 7, right? So according to what you told me, right, we got these two pre-order in order, right? We go to 3, 3 goes here, go here, then we check 11, right? Is 11 checked or unchecked? Well, this is unvisited, so we said 3 to 11. Because now 9 is not next to 3, right? So how do we determine which is the left, which is right? Is it 11? Is it 9? Is it 10?
Yeah, that makes sense.
Yeah, and I mean we can skip
3.
3, right? And we'd say like, let's go to 9. 9, yes, yes, right? We got 9. 9 has 10 and 11 over here,
Uh,
right? Let's go to 10, right? So 3 is a 9, right? So we got 3 and then 9 and then its children, right? So this is the left of 3. Then we go to 10, right? 10 has no children and 9 is visited, so 10 is by itself. Is this the right of 3 or the left of 3 or the left children of 9? How do we determine this 10? Because over here, how it looked like, it would be 10 and 11, right?
3, 9, 10, 11, 20, 15, 7, 10, 9, 11, 3, 15, 20. Yeah, that
Yeah,
is
that's
valid.
it.
That is
That
valid.
that's the only thing. Is like, how are you gonna determine which is left, which is right? Because I don't know, and I'm not trying to like push. I feel like I'm shaming you or anything. No, I'm
Dude,
sorry, my guy.
I feel like you're bashing on me right now.
No, I'm
And
sorry,
like
but
you hate
no,
me
no,
and
no,
you
no,
want me to die.
no. What do you mean? No, no, no,
I'm
no.
joking. No, no, I honestly I don't mind. I'm that's why we're here for.
Yeah,
We discuss our approaches, and if it's wrong, it's wrong. It's not a big deal. But
yeah,
I'm glad that you showed that we got to see an example because I wasn't
yeah,
understanding it before. I was like, I thought you were talking about like, oh, how do you connect 3 to 20? But no, you're right. If there's some more nodes like this, then
yeah,
in the in order form, those kind of um, get in the way between the actual left child of
yeah,
3 and then
yeah,
so how would you how would you determine, and I guess it would be more annoying to do that approach that I was saying because I'm sure maybe you can figure it out.
yeah, for sure.
You
Yes,
could
yes,
say
yes.
keep going until you find this node right here, one that's
Yeah,
next to 3, because that means that's a child. So you could be like, okay, here, keep going. Is 9 right next to it? Eventually, yes, it is. Or I don't know. Maybe there's something like that,
yeah.
but
What
no, I
makes
get what you're saying.
what makes this problem difficult is that we're not given the nodes. Like, what nodes are nodes or that are empty? Because if they were empty, that would make like the work super easier, and we just have like we like I said, we could use like the formulas, the 2 times I plus 1 plus 2,
Yeah,
and we can get those. But since they don't have nodes, it makes it a little bit harder to
yeah.
know which one is which. But yeah, and also my approach, I don't know if it's right. So if you see something that's better, you tell me, brother. You bash on me.
All right. So
Alrighty.
we got what we want to do.
I think so. Yes. And first shield, welcome to the stream, brother. Welcome to the stream. Thank you, brother. Thank you for the encouragement. Yes, this is what I think we should do, but I'm not sure how. I'm not 100% this is gonna work, but we'll see. We'll see.
All right.
Yep, yep.
You want to put it into the to LeetCode already?
Yeah, if you're down, yeah, for sure. For sure, for sure.
So we want
Mm,
to how do you do it?
uh,
There you go. Comparison approach. Start at pre-order pre-order I,
yes, yes,
and
yes.
then mm, from there you do
Okay, I'm back.
What
I'm
was
back.
that?
I'm sorry. I'm
Okay,
sorry. I'm
what's
sorry.
up?
I'm sorry. I'm sorry. I'm sorry. So
Uh, zero.
I finally understood what self meant.
Self meant.
Yeah, on the Python, I finally understood what it meant.
Mm,
While working on the architecture project, our teammate uses it a lot, and I was like, all right, what it is? It's basically it tells you the scope of the variable, right? For example, if I declare self variable one,
huh?
right? That adding self would allow it for the other functions, right? Even though they don't have variable one declared in their scope, access that value. So it's like you say like anywhere you be in a constructor per se, you right? You put a constructor, you so self variable one, self variable two, self variable three. You know how in Java we do the privates, private for Android for applications we do private array list or private, I don't know, property name, and then the constructor we say property name. This dot property name will equal whatever the parameter is.
Yeah.
Yeah, it's the same thing, but instead of saying like private, all that, you do to self dot with the name of the variable equal to whatever, and now all the uh all the methods and functions have access to the variable. So it's just to make it like outside the scope for the entire class. So that's a pretty neat thing about Python. You just have to do
Self dot.
self dot variable name, and it'll be accessed through the entire thing.
Okay, okay.
Yeah, because I remember we mentioned it in the previous times where like what does self mean? What self
Yeah.
means to the build tree, and if you want to call a function inside of the class, where you do self build tree, and you will call the function build tree.
All right.
Yep, yep,
That's good
yep.
to know.
This is yes.
Okay, so tell me if I'm understanding this right. We're gonna start at this. You're gonna call the function. I mean, you're
Uh
gonna
huh.
recursively call. I don't know if it's pre-order or something else, but something along the lines of this,
Yes.
something like that.
Yes. 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 Yes.
So guide me from what you're
Okay,
thinking.
so we're gonna say first we're gonna use build tree as a function. We're not gonna create no function, no anything. We're gonna use build tree, def build tree, right? So our base case is gonna say since we're cutting away from the list, our
Mm-hmm.
base case is if we run out of elements.
Yes.
So we're gonna say if pre-order, if not pre-order, how do you say? If pre-order, if pre-order, and then check not I just the length, or if pre-order, if not pre-order, I think that checks if it's empty or not,
Just a
and not
function like that,
and yeah, or not pre-order.
or not.
Yeah, or not pre-order.
I don't get this right here.
Well, that's the base case.
But if not pre-order or not pre-order,
Yeah, if in
that's the
order.
in order. Okay,
Yeah.
in order. All right.
Yeah, so that'll be our base case, and if that's true, we just return none. Like, there's no more nodes to do. There's nothing. It's just we're empty. We're
Yep. Yep.
gassed out. Right. And then, is this a pseudocode?
Yeah. Yeah. Yeah.
Yeah.
I'm
Okay.
just
Okay.
trying to
Okay.
write down the general idea you're talking about.
All right. So it's not a function. It's just the actual list. So we
Yep.
don't have the parentheses. For like line 13. Yeah, those. Is yes. And here we're gonna determine, right?
Mm-hmm.
Line 16, right?
I don't know if that's right, but okay, go.
So I have to admit, I I looked at a solution how to do this. So because I know we spend not last stream, but previous stream, like a good amount of time on this problem. So, you know, I think I understand the solution. So if you see that
Okay.
this solution is similar to another solution, it's because of that. I come clear. I come clean. Come clean. I come clean. So I'm
I'm
no
glad you came
genius,
clean. I'm glad
but
you
I'm
came
coming
clean.
clean, but I'm coming clean, right?
All right.
So, but it's for the sake of like learning the problem. Because if we stayed here, we would be gone in circles. I feel like I've gone in circles. Like I
Okay.
would have gone in circles. So we already gave it a good amount of time, like 40, 50 minutes or an hour. Previous stream, I think we're good to like understand how to do it and to learn why is it working, learn new tools, learn new logic, and learn new stuff that we can like consume or add to our
Right.
toolkit for other problems. So yes, I come clean.
Okay.
Don't cancel me.
I'm glad you confess. I mean, that's
Yeah.
good, man. Uh, now maybe I don't know. Never mind. I don't know what I was gonna say. I was gonna say like a joke, but I didn't know what I was gonna say. Okay,
Yeah.
keep going, keep going.
So if not pre-ordered, right? So we search. So if it's none, we one of the list is empty. It doesn't matter, right?
Mm-hmm.
It's good. Now we have to find the root. Like we said, the root is gonna equal to the first element, right? So
The
we're gonna
first
go root
element of pre-order.
of pre-order. Yes.
Yes.
Right. So we got that, right?
Yes.
So now
Yes.
that's three. That's three, right?
Yep.
Then we're gonna find the mid, or we're gonna find where in order is that three at, right? Because we want to split the tree between the left side of three and the right side of three, right?
Okay.
Right. So to do that, we're gonna find something called dot index, and dot index is pretty cool. So we're gonna do mid will equal, right? So like midpoint, mid will equal in order, the list in order,
In order.
dot index
Dot index at pre-order 0.
at pre-order 0. Yes. And I forgot about something. We're gonna create a tree node on line 16.
Line 16.
You're gonna wrap pre-order and the curly bracelet in a tree node. Yes, tree node. Uh-huh. Yes. So now
Okay.
root is equal to an object or an instance of tree node,
Yes.
right? So it's a value. It has a left node, odd stuff, all that good things, right? So now we
Uh-huh.
find the midpoint.
Now we
Now the
find the midpoint.
left. So now we're gonna go to the left side, right? To the left side. So we're gonna say left. We're gonna do the root dot left, right? Because now we're gonna say root dot left. Yeah, because we want the left of the root to equals to one of the nodes in there, right? To one of the nodes in there.
Okay.
Yeah. So we're gonna be self dot build tree.
Oh, you being serious right now?
Yeah.
Self dot build tree.
Yeah. Because why? Because we're calling the function build tree. Because if you say build tree, what Python is gonna do is gonna look at the function and be like, hey, you have no build tree, no variable build tree initialized there. If
But
you do self dot build
but
tree,
if we've done recursion problems before. We never put self.
well, because we've declared our own functions. Here we're using functions at line 8, build tree, right? And we use recursion because we always declare it outside the function. We always do
Okay.
DFS, we do other logic, and then outside DFS we say, hey, DFS, let's call on DFS. And Python is gonna see like, hey, we do have something called DFS, which is a function. Over here, inside the scope, we have no build tree. And I might be wrong.
Alright.
Right? I might be wrong. But that's how I think it. That's how I think. So, no, we're not creating we're not creating a new tree. Tree node. No. We're just setting it to the whatever. We're just sending the self-built tree, right? Then we're gonna send. Here becomes the magic. Pre-order, right? Square brackets. Inside we're gonna do 1 colon mid plus 1. So what I think this does, right? It's saying grab the 1,
Hold on, this
grab
turned
the
from pseudocode to actually writing the code. So let me just get out of here.
I was
Let me
gonna
just get
tell
out
you
of here.
something. I was gonna say the same thing.
I thought we were doing pseudocode. This is This is the solution.
Hey, you started typing. I was like, hey, I'm just telling you what we're gonna do.
Hold up. Don't tell me. Mid. Don't tell me. Don't tell me.
No, I'm not telling you. I'm not telling you.
Yes. Mid to. Oh. No. Oh. Can you do that? Ooh. Or you don't even need to do that. You just do that. Ooh. Maybe. We'll see. We'll see what you say. Okay.
So it is
Because you want to
okay,
go the
so
mid to the end.
mid to the end. Exactly.
Yes.
Exactly. But this is pre-order. I haven't fully really understood this thing. Wait, give me seconds. 0, 1, 2, 3, 4. Okay. I'm not really familiarized with this syntax, but I think I know what it's trying to do, right? But the pre-order one, the
Starts
first
at
one, that
1,
one,
and it
it's
goes all
no,
the way to mid.
mid plus 1, but it skips 1 though. It skips 1.
Oh, okay.
It skips
So
3.
it's exclusive.
Yeah, it's exclusive. It skips 3 because we already took care of 3 already. And then we go mid plus 1, because mid is gonna give you the position of 3 inside of in order. So for example, over here input, in order it's 3, so that's gonna give you a 1, right? Right here, yes. In order is gonna 3, right? It's gonna say 3, that's 1 in order of 1, right? So mid equals 1. Now we go to pre-order, we skip 1, so we skip 3, and then mid plus 1, I'm pretty sure that excludes mid plus 1, so it stops at 9. If I'm not
No. That one's a little tricky. Because I remember that
yeah, they're exclusive.
Both of them were exclusive?
I think so.
Because I remember. Oh, maybe
wait a
that's
minute.
different function.
Well, okay, never mind. 1 is inclusive. So you start at index at 1, which is 9. So we do skip 3. Yes.
Yep.
So we include 9. Mid plus 1, right? So mid is 1 in order. Plus 1, that's 2. But we exclude that plus 2, so it's just 9. So we exclude that 9. Because the mid plus 1 is 2.
So you
it's
start
0,
off
1,
at
2.
1. You start off at 1.
You start off at 1.
You don't skip. You're not skipping.
Yeah, you start at 9.
The end is exclusive.
Yeah, so you exclude 20.
Yeah.
So it's 9. Yeah.
Yep.
Mid over here, you remove a colon.
Remove a colon.
And if you remove a colon, right, and it's mid plus 1, it's now mid, because then now we're starting at 2, which is 20. Right, because mid is 1. If we do plus 1, that's 2, which is 20. And now mid plus 1 colon, it's get from 20 all the way to the end. Yeah or nay?
Oh, so colon just goes all the way to the end? You don't need a double
colon? Yeah, colon goes all the way to yes.
Okay, perfect.
Okay, so that's a pre-order. We still need the in order. In order, so we're going to do the save build tree, the same function call, right? We're just going to add a comma. On pre-order on line 21, inside the parentheses, add a comma. do in order, colon, colon, mid. Yes. So this what it's gonna do is gonna grab all the everything until excluding mid. So it's just gonna grab 9 and excluding 3. So it's gonna go 9, 3, but you exclude 3 because it's exclusive, so you just grab 9. Yay or nay? Because now we're just getting the left side.
Then why are we grabbing the... Oh. Why are we grabbing this pre-order then?
Because that pre-order is gonna help us determine the values, right, of the left side too. That pre-order, right? That pre-order is gonna help us determine what the how do I call it? The not the sequence, but the order of how the notes were placed on the left side, right? For example, like I said, if we have 9 and we have 10 and 11, right? 10 and 11 are still nodes that might have
Where are you getting
children.
10 and 11 from?
Well, from the example we did, right? From 10 and 11, right? We still have to get those nodes and check whether those 10 and 11 still have nodes or have children, right? So it's like in both of the arrays, we're getting the left and right sides in both of the arrays. Pretty much, we're both getting both in the arrays. The left nodes and the right nodes.
Okay.
Yeah, that's why we're getting the pre-order, right? And then in the in order, we're gonna do the same thing: mid plus 1 all the way to the end. Yes, there you go. Yep. And now we return root. Yes. So basically what this thing is doing is saying like, all right, let's go to 3. 3 left node is gonna go to 9. So we go back to 9 on top, right? Because 9 is going into the build tree. 9 root is 9. Mid we go pre-order of 9, which is 0 in this case, right? And we grab from what is this called? Okay, yes, from 20, I think. No. It works good for the first time, but then after that, I'm gone. So I have to trace it down. But it does make sense.
So, let me see if I could grasp this. I understood it visually. I'm trying to grasp it now.
Yeah.
You start with pre-order 0, 3. You create, that's the root. You say mid is pre-order 0 at the value of pre-order 0, get the index of it in the in order. So that would be 1. Mid is 1.
Yes.
Root.left will be a recursion call of build tree where we pass pre-order from 1, which is 9, to mid plus 1, which will be just 9.
Just 9. Yeah.
Pass 9 as a pre-order, and as the in order we pass
9
from all the way to mid, and mid is 1, so, and it's exclusive, so that means it's just 9. So we pass in both 9 and 9. Now we're gonna say at pre-order 0 is a root, which is 9. At index 9 of no 9.
Yes.
What's the index of 9 in order? And that you only pass 9.
Yeah, so it's 0.
So it's gonna be 0.
Yeah.
So now you're saying you're going from 1 to 0. That's not gonna work.
Yeah, I think it's gonna return an empty list.
This is empty, and then this would be empty. So you
Yeah,
say
because it's
if
0.
not pre-order, then you go back up,
Mm-hmm.
and then you go from 0 plus 1. Again, there's no other thing in pre-order, and then there's no other thing, because remember it's still 9 to 9, correct?
Yes.
Okay. So there's nothing.
Yeah.
So then
So
returns none. Boom. And now we're back over here.
yeah.
Oh.
Oh.
Now we're back over here, and our array is back to this one.
Yes, but now for yes. Yeah.
Back to this.
We're mid is
So mid is 1 still. 1
Yes.
pre-order of 2 all the way to
Which
the
is
end, which is 0, 1, 2. All the way
20.
to the end will be 20 and 15.
2015 and 7.
But I thought this is oh no, it's not. Okay.
Yeah.
So 2015 and 7 will be pre-order, and in order would be 2 0, 1, 2, 15, the same thing. 15,
Yep.
20 to 7. So now pre-order in order are those. And then you say pre-order 0, that would be 20.
Mm-hmm.
And then at 20, what's the index in order? That would be 4, 0, 1, 2. Sorry, it would be 3. 0, 1, 2, 3.
I think that's based on on those 3 numbers. 15, 20, and 7.
Oh yes,
So it'd be 1.
It'll be
Yeah.
1. Okay, thank you for catching that.
Of course, no worries. I got you.
So it'll be 1. And then from pre-order, from 1 to 2, 0,
Which is
1,
15
2,
and 7.
it'll just be 15.
Yes. 15. Yes.
And
My bad.
then for in order, it would be from 0 to mid, which is just 15.
Yes.
Right? Because mid is 1.
Yeah.
Is that correct? Okay.
Yeah.
Whew, hold on. I'm doing good so far. Hold on.
Yeah.
Now we pass 15 and 15. You create the root. 15, 0. This is not going to do anything, I don't think.
Yeah, because it's
none.
like it's gonna happen like with 9 too, like where there are just gonna be empty.
Did we create a node for 20 already?
Yeah.
Yes.
Number 7, line 17 creates a node.
Yeah, but I think we did. Yes. Okay.
Yeah.
So then we create a node for 15 now, and then we're doing this one. And oh no, sorry. You do this one. It's return. I just lost it.
No, yes. You're still in 15,
We're
right?
still in 15.
We're still in 15.
15 at 0. Our mid is 0, so these will not work, right?
Yeah, this one won't work.
So when you go in these,
it's gonna return none. Yes.
And then you try these.
And it's gonna return
none.
Yeah.
So you return root,
which is 15.
Which is
right?
15.
So
and were we on this one?
Yes, we're on that one for 20.
So that means root dot left.
It's 15.
Okay.
Yes. Okay. So now we go to the right.
Now we go to the right.
Yeah.
And mid
is
1 is 1, 2. So at 2, 0, 1, 2, all the way to
7.
end is a 7. And then mid plus 1, which is 2, which is same 7 all the way to end. It'll be 7, 7. All right. Create a node for 7. This will be 0.
That'll be 1. That'll be 0. Yes.
This one work. This one work. You return it. It's root dot right. 20.
Yes.
Return root. All right.
Yeah. Pretty much. You got it.
All right.
Oh, but it's damn, that's crazy.
I'm actually surprised that I was able to trace that.
You did good, bro. That was all you, bro. That was all you, bro. I was letting you ride. You were zooming. All
Dude,
right,
trust
brother.
me. Whenever this break hits, we're gonna get on Factorial and we're gonna be grinding that. We're gonna be making factories. We're gonna be conveyor belts, everything, and up and down and left,
Hey,
right,
I'm
and we're gonna
talking
have
8 hours,
robots.
bro. 8 hours,
Eight
bro.
hours a
Boom, boom,
day,
boom, boom,
full
boom.
time, full
Oh,
time.
full time.
Yeah. And what's the benefit? Is we're gonna learn how to trace better. We're gonna learn how to think in our heads
How
and
much are the
computate everything.
DLCs?
Oh, I don't think we need to do the DLC.
No, okay, okay, okay.
Um,
With the basic game, it's good
35.
enough.
Yeah, basic game you could do. I haven't even beat the basic game. So,
All right, fair, fair,
first
fair.
shield. You can't see if it was accepted. Yeah, we haven't tested it yet. We're just we were tracing it to make sure we understood it. But all right. You think that was?
I
You want
think
to run it?
so. Yeah.
All right. Let's see. Woohoo! Oh, okay. My bad. My bad. All right. Try it again.
Hey,
Try it
bro,
again.
come on, yeah, come on, brother,
Try
come
it
on.
again. Try it again. Try it again. My bad. Let's see. Let's see.
SMH, SMH.
Okay. 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 So far, so good. Let's see. Is there any other test cases? Um,
Oh, right there. Woo, fast. Baby,
wait.
hot
Is that
chocolate.
already what we have? No.
Yeah, 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 yeah.
Wait.
It's
Is
the
it?
second one.
No.
Oh no, 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 no. Yeah, my bad, my bad.
Right? Come on, man. Let's get it.
Sorry,
Let's
my
get
boy.
it. Boom. Boom. Uh-oh. Wait, can't you only do 8?
Not sure.
Run it.
We did it!
Yo, what's
We
up with
did
this glitch?
it!
What's up with this bug? This happened last time as well. It says 0
Bro, you
runtime.
just try to find some bugs, bro.
I'm just
Leave
saying.
LeetCode
I'm just
alone,
saying.
bro. Let LeetCode,
Like,
bro.
bro,
You're
look.
hot.
They're adding new features of like how many people are doing this, right? But they can't fix this damn bug. Like, obviously, this ain't the runtime. Or maybe I'm not. You want to
Damn,
submit? We're
bro.
submitting it.
Man, he's hating
We're
on
submitting
LeetCode.
it.
Uno, dos, y
Good
tres.
stuff. Oh, look, see, look. It tells us the estimated runtime, but it doesn't tell us down here. Come on now. Fix that, man. Fix that. Oh, but wait, though. They want to tell you how many users are on the problem, though. They want to
Yeah.
make sure they got that right. But
Maybe,
no.
maybe it's the runtime for the test result. And since it's like pretty, the test results aren't that complex, right?
But the
All
thing
right,
is,
yeah.
we've never had it. We've never, in our experience, it would actually show something.
I don't know. I think it's just hunting for a mistake.
Yeah. Anyways. All right, good stuff
Oh
on that
man,
one. Good
let's do
stuff.
some insane levels. Let's
Okay,
update
insane
those
level, insane
numbers.
level. Where are you at, man?
Oh
Where you
man,
at?
I'm like a 4 or 5,
4 or
dude.
5, 4 or 5,
Yeah. I'll take 5, 5, 5.
5, 5.
Yeah, it's starting to settle in. Right, this one.
I'm gonna give myself a 4.5. I'm there with you. I'm there with you.
Yes, sir. Yes,
I'm there
sir.
with you. Okay.
You wanna try one
Yeah.
more
Yeah. Let's
and
go.
see if we can do it?
Okay. I
Yeah.
don't know why it doesn't show I'm logged in. Let's fix that.
Come on, brother.
Boom,
Log in.
boom. All right, perfect. All right, everyone. Sorry that took an hour and 20 minutes or so.
But it was an hour and
But-
20 minutes where we actually like learned.
But we learned.
Yeah. We know
learned
that's. I
it.
feel like that's the main approach of these things, where we learn why it works and how it works, and me personally, I learned a couple new things. I learned how to play around with arrays, the self thing, and how improve my recursion a little bit with this problem, and how do the pre-order and in order work with them, like with it, like with how they correlate to each other, the different traversals. I don't know about you, but that's what I learned in that
I learned
problem this hour.
that. What did I learn?
Ooh, almost
I
fell.
learned more about the self dot function call. Um, I learned that Jose will always find a counterexample to my approach.
No, what do you mean?
And
Nah,
I learned
nah, bro. What do you mean? No, oh man, bro, throwing me under the
Jose says,
bus.
Jose tells me, you always try to find a bug in the. Well, that's him. That's what he does to me in my
Nah, nah,
approaches.
nah,
You
no,
always try to
no,
find a
no,
bug in my
no, no, no,
approaches.
no, 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 no,
So I
no,
don't want
no.
to hear it with
No,
you
no, no, no,
saying
no, no, no,
saying,
no, no,
"Oh, I'm
no.
always
I
trying to
don't, I
find a
don't find a
bug."
bug in our approaches.
Yes, you are.
It comes like you. I'm just thinking. I'm like, well, what about this? I'm just like thinking about it. It's not like, oh, that's a bug. It's not gonna
Well,
work because
that's
of
what I'm
that.
doing too with the LeetCode. I'm just
I
thinking, like,
know.
why isn't the
Just
runtime not showing?
no. You're just saying like
I'm just
you just said
thinking.
you're looking for. I see you like scan the page like inch by inch, like with a ruler, just trying to see like if there's a bug in there.
Yeah, man.
I get that. I get that.
Yeah, no, I thought it was good. Also, I thought the tracing was really nice. It
Yeah.
brought it all together. Um, so I would say that. But anyways,
Alrighty.
I'll read this one.
All
I've
right.
never
Yeah.
seen this one before. We might need to use some guide. We might need some guidance from
Some
people in the chat or
inspiration.
some inspiration from
Yeah.
online database that could formulate sentences. Um, so we're gonna try to use whatever we can to solve this one. Hopefully this string. But anyways, 1, 2, 4 binary tree maximum path sum. This is a hard problem, and it is a path in a binary tree is a sequence of nodes where each pair of adjacent nodes in the sequence has an edge connecting them. A node can only appear in the sequence at most once. Note that the path does not need to pass through the root. The path sum of a path is the sum of the node's values in the path. What the? Okay.
Yeah. For example, like if you go down, that's the path sum.
Yeah.
Like from 1 to 2. Yeah. Yeah.
Given the root of a binary tree, return the maximum path sum of any non-empty path. Okay. Yeah.
Whoa.
That's
Whoa. Whoa.
hip.
Whoa. Whoa. Whoa.
That's hip.
Why is it
So
6?
I'm gonna read this example.
Hmm.
That doesn't mean I understand it. I'm just gonna simply read it. So for example 1, we have an input of 1, 2, and 3, and the output is 6. The explanation is because the optimal path is from 2 to 1 to 3, with the path sum of 2 plus 1 plus 3 equals 6. Example 2, we have input of -10, 9, 20, no, 15, 7. The output is 42. Explanation is because the optimal path is from 15 to 20 to 7 with the path sum of 42 because you add those up. The constraints: the number of nodes in a tree is in the range 1 to 3 times 10 to the power of 4, and the node value will be greater than -1,000 and less than will be greater than equal to -1,000 and less than equal to 1,000. Greater than equal to 1,000. Yeah. Anyways.
First shield is scaring me. He said, "God damns, this one is hard." Bro, first shield,
All right.
bro. I'm trusting you, first shield. I'm trusting you.
So.
Oh man.
Okay. Let's pick
What's
it
a
apart.
what's a pet sum again? Like, it's a node in the sequence has an edge connecting them. Okay. Ufas. So as long as they're connected, it's a path.
Yes. But never mind. Yes.
Not sure how to work this one.
But you can't go back. Like, you can't do 15, 27, go back up to negative 10, 9, right?
You
It has
can
to,
with recursion.
but what, but like the path, like the definition of, like, doesn't the definition prevent us from like going to, like, it's a path, so you can't go, can you go back and go?
Well, according to the path on the top, it says like they just have to be connected. Binary tree is a sequence of nodes where a pair of adjacent nodes in the sequence has an edge connecting them. So they're just being like connected. For example 1, the reason the output is 6 is because you have to 2 plus 1 plus 3, which equals 6. Oh, Firstio, he couldn't solve this one. Oh no. Oh, Firstio. Here, this one's 42 because it's 15, 20, and 7.
So you're saying there's maybe a way that let's say this wasn't a negative 10. Let's say this was a 5.
Mm-hmm.
Could you go 15, 20, 7, go back, not counting 20 again, but go back and hit 5 and then 9?
Yeah.
Or you only got to
Oh, you
one
had to
way.
start at 10.
So
You had to,
15, 20.
it's because you have to start at 10.
You don't have to start at 10. I didn't do that here. It just finds a path.
Well, that's the thing. Because you have to start at 10, you have to keep track of the different paths and determine which one is the biggest one.
Well, I know that, like, in code wise, but. Oh, that's what you're talking about.
Yeah, like you might start at
You would
10.
have to start at root either way.
Yeah, like negative 10, you go to 9, that's negative 1. So that's not. So you store negative 1. You go to 9. Well, 9, I think it's no, it's not a path. So negative 10, 1, that's a negative 1. Negative 10 to 20 to 15, that's 25. Negative 10 to 20 to 7, that's 17. But you can do, all right, I don't care about this negative 10, and we can have a path from 20 to 15 to 7, which is 42, right? So you can like include them or exclude them as well. Like you don't necessarily need to follow like the paths, right? You just have to find the path where the nodes are connected that equal to the highest sum. For example, 20.
But would that still count though? If, like I said, if this is a 5 and you're starting,
I mean, if it's a 5, it will count. The entire path is going to be
I see.
Yeah, it's gonna add the 42 plus a 9 plus a 5.
So let's say this was a 5. Would the path? Okay, look. If this was a 5, would the path be? Could you do 9, 5? Okay, 14 plus 20. What is that? 34. 34 plus 15. That is
49.
49. And then can you go to 7 though? Can you go 15 back to 7?
Yeah.
But the path would be 9, 9, 5, 20, 15, back to 20 to 7.
Yeah. I mean, we've done it before. We can do in order, pre-order, post-order, right? In order, we check
It's talking about adjacent nodes, or yeah. It's an
I
edge
mean,
connecting them. So what I'm want to get clarification on
oh, okay, I see, I see.
is like, will that 20 count again, or can we ignore it, or would that path still
I
work,
mean,
or should we, or if you're going one way, you can't go back, like you can't revert back to go to a different way.
okay, so adjacent nodes being that they're connected by a
Path,
parent-child
the
relationship.
edge, the edge.
Yeah, by a single edge. For example, -10, the path would be to 9 and to 20.
Yes, because it'll be 9, -10, 20, right?
Yeah. And to answer your question, we can do a pre-order where we visit the 20 first, then the 15, and then the 7, and then we go back to 20. But we first add the 20, then 15, 7, and as soon as we go back to 7, we just return back to -10. Right?
No,
Just
I
because we
get I get
visited.
what you're saying. That there's you could do those traversals, but the question itself wants a path. So that's
Yeah.
the path. If you're following the line, a normal line, like a not ignoring that there's pre-order traversals in order.
Yeah.
Um, it wants a linear path. Like I'm wondering, does it want a linear path to where it's this node and the next one is this one and the next one is 7, and then you can't go back. You can't go back to up because the path would then be 20 again and then -10. Like, because that's the linear path because it's saying 15,
Well,
27.
we're s- we're not returning the path itself. We're just returning the sum.
Yes, but it's using path as a definition. Like
Yeah, it's a path
we
sum, right?
want a
So we can
path sum.
we yeah,
So
we
is
can
that considered a
do
path? Is 1527 going back up to -10, or like
well. Yeah, I get you. I get you. Well, in this case, right? We can do 15, 27, 42, store it somewhere. We go to -10, right? And we just focus on 9 and 20. Like it's not gonna go, oh, 15, 27, then -10. No, we just go with that little triangle, the 20, 15, and 7,
but
right?
you can't. But any future node that you go, like how you're saying, you can't add it to the 47.
No.
Yes. Okay. Perfect.
Yeah. Yeah, yeah.
Yep.
Because it's just like I think it's adjacent.
Yeah.
So it says every node which is not the root has exactly one adjacent node above it. A tree binary if every node has at most two adjacent. Oh, okay. That's uh. bu- 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 bu-
So with that being said,
uh, So I don't know if we count -10 as an adjacent node. But I don't think so though. I don't think so. Because if we did count them, well, -10. All right, let's think it through. -10, 20, that's 5. Okay. Okay, yes, yes. So we have to count -10. Oh, I don't like this. I don't like this.
okay. So what's the traversal that does 9, -10, 20,
That's
and then it
post
goes
order,
15,
pre-order,
27.
pre-order.
That's pretty okay. I'm just throwing stuff. You
Yeah,
remember
yeah,
the analogy? The you're when you're checking your pasta to see if it's ready, you throw it at the wall, see if it sticks.
yeah,
Okay, that's what I'm doing right now. I'm just throwing it
yeah,
at the
yeah.
wall, see if it sticks. Um, so if we do that, right? We do we add 9, -10, 20, and then we're like, oh, okay, that's That's 1.
Mm,
Is that right? No.
19.
That's. Oh my gosh. That's crazy. Okay. 19, right?
Uh-huh.
Then we're checking the 1527, right? Right. If 15 gives us a greater sum than just adding 7, like if it's 9, negative 10, 20, 15, if this sum is greater than 9, negative 10, 27, then choose the bigger one or whatever, right? And then also you're checking the individual subtree 15, 27. If that's greater than the one you just stored previously, then return that.
Mm-hmm.
I don't know. That's just an idea. Because they're starting at the top, right? 9, negative 10, 20. And we don't want to stop. Or I guess we could store that. We could store the first 3, boom, store it. And then we're like, okay, let's continue going more. We know the next traversal would be this one. And that it's going to be the new subtree. And we know that that's technically this left child is still connected in the path, but you can't add these two and say they're still connected in the path.
Well, 15 is not connected to 9.
But it's 9, negative 10, 20, and 15, which is
Uh,
still.
I think what adjacent means is that there's one edge that connects them directly. And 9, you have to go through 10 to 20 and then to get to 15.
Yeah.
For example, 20 here, there's one big one, which is negative 10, 15, 7, 20. That's the neighboring adjacent. Then there's 15, 7. There's 15, 10. And there's 15, 20, 15, 10, 15, 7, right? And from all those, like all those possible adjacent paths, we have to choose the biggest one. A path is a binary tree in a sequence nodes where each pair of adjacent nodes in the sequence has an edge connecting them. So we have 2 nodes and there's an edge connecting them. But I'm not sure.
Where each pair of adjacent nodes in the sequence has an edge connecting them. Chihuahuas.
I don't like this.
I don't like you.
What do you mean, bro? Why me? Always me.
Huh. Interesting. Interesting. Oh, look, there's a promo code available.
Click on it. Let's see what viruses you get.
Nope, I'm good.
Is there topics?
Oh, that's great.
Dynamic programming.
Okay. Think about it. Remember what Professor said.
To be or not to be? That is the question.
Professor said, assume you know the solution, or you know the. What was it?
Assume it's assume you know the solution. Yes,
Assume
and
you know
then
the
the
solution. How
dynamic
would you? How would you? I remember. I visually remember the. You had the he had the
Hmm.
function, and you assume the function works. How would you structure it from there? Something along the lines of that.
Trying to think.
You might be cooked. I hate to
Might be
say it.
cooked.
How about we use some inspiration for this one?
I think we can do it without inspiration.
Oh my gosh.
Come on,
All right.
brother.
I'm here with you. I'm here with you.
Mm. Well, my brain is getting fried by the second. Trying to think over here, but I don't.
I'm here with you. I'm here with you.
I'm sleepy. I'm sleepy Joe.
I'm here with you. I'm here with you. Similar questions? Have some companies? Nope.
Go to Petsa. Maybe we can do. Hmm.
Interesting. Interesting. What do you need? What do you need to see?
No, I just want to see what like that definition of Petsa was
Oh,
here.
okay.
Is there a Petsa medium? There we go.
Why aren't we getting this one?
Not sure.
Why are we getting the hardest one? Just we did the first one. Why? Ooh, you're getting me upset already. Who do you want me to be?
Trying thinking, brother. Trying to think. You want to do this one? Or you want to do the other one?
How
Dude,
about
my
we flip?
friend.
How about we flip a coin?
You tell me.
And in the moment that the coin is flipping, if we favor an option more than the other, then we'll just go with that.
You tell me, my guy.
I'm gonna flip a coin. Pass some two is heads. The
Medium and
other
hard.
one.
Call it medium and hard. Medium and hard. All right.
And wait, where's the other one? Okay. This one's tails. This one's heads. What did I
Which
say
one
was
was
right?
heads?
I
I don't
forgot.
know. I was gonna ask you.
Oh man, I
All right. Let's
forgot.
say the hard is heads. The medium is tails. Hard is heads. Medium easy. Medium tails.
Tails, heads.
Yeah.
Heads, tails. Okay.
Oh, we're
All right.
cooked,
That's
brother.
fate. That's fate. That's fate, man. We can use a little bit of inspiration, some
You want to?
guidance, some guidance.
I mean, well, I got you. I got you.
Like a just you know how like for essays they give you like a little outline and stuff like, oh, talk about the story here, and then bring up the critical points, paragraph 1, 2, and 3, and then at the end conclude it back, like stuff like that. That's kind of we need a guideline to solve this.
Oh wow.
What happened?
So anything can be a path.
You lie.
I think so. Let me. Oh my god. I think so. Cause it gave me an example. I'm gonna probably put it in Skelly Draw.
Okay.
If you want to see it. Oh my god, bro! Just put it here. My god.
Bro, hold on. I you know what? I know we're live and stuff, but I hate. I'm not gonna say no names, but but you know what I'm talking about if I doing it. They're like well then how would you, oh well then you're gonna just do this and A equals R, and bro, like erase the rest of the stuff, bro. Like I
Oh
can't read it,
man.
bro. Anyways, I'm sorry. Okay, I'm
I
here.
think I think I know. I think I know. I think I know.
All right, I'm here. I'm here.
So here, 4, 2, 3. It's a path.
4, 2, 3.
I don't know how. I don't know when. Where? What? no, it's yeah. It's right there. Right there.
Huh?
Yeah.
4, 2, 3. Aw. How is that a path?
We'll see.
I mean, if one is in the middle, I mean, if you're passing through one, then
Okay,
yeah,
so
that's a path.
it said that it's not a path anymore.
Oh, what happened to the music?
Yeah, they basically have to be connected by an edge, pretty much. Um, dude, I don't know how to even approach this problem.
that a nuke? Going into the what is that? Oh, that's crazy. Yo. That is funny. That's us doing LeetCode on our computer. That is crazy, man.
Oh man,
We're cooked.
we're cooked, brother. We're cooked. I mean, it's because I don't know how to approach this one. 'Cause a path. Let's see. How to determine a path? Oh, you hungry, my guy? Man is
What's us?
cooking vegetables.
We're cooked, man.
Oh, we're cooked.
Anyways, keep going.
It's because I don't know. It's gonna be hard to like know which one is a path.
As soon as it said dynamic programming, I kind of just
Blanked
spaced
out.
out. Yeah, like
Yeah.
spaced out. How about let's go
I
into
mean,
discussion. Let's see.
let's see.
Let's see what they be. Let's see what they're saying.
Yeah. Let's see. Let's see if we can figure out something.
All right. Oh, perfect.
That's us.
Um. Oh,
So people are saying are
do we read this?
all right. Description of algorithm.
Okay.
Create a source node S. Create a direct edges with weight 0 connecting from S to every node of the tree. Create a sync node S. Create a, okay. Every node V, including the root it leaves, we create two nodes V1, V2 from each. Huh? The heck?
TLDR. What does that mean?
To be determined.
TLDR.
No, too long. Didn't read.
Oh, that's funny.
Too
That
long. It
is
didn't read.
funny. But
Oh,
what is
that's.
this? That's it.
TTR. Didn't.
Uh,
Oh man, TODR. I'm gonna start using it.
that is crazy.
Oh man, TODR. Too long.
Is that actually true?
No, I have it over here.
You searched it up?
Yeah, too long didn't read.
That is crazy.
I'm gonna start spamming that too on my messages, even though it's just like a simple message to TLDR. Too long to read.
Then what
Oh
is
man.
this? They're kind of contradicting themselves. Not kind of, they are. They did the whole. This is too long, can't read. That's crazy. Easy question. Where do you see that at? Anyways, do you want to read this part?
I mean, yeah. Having non-correct information requires transfer the graph. Given the graph comes from negative values, trying to translate problem compared solution as to probably has negative cycles. What is such on the previous point of view that used to go up? Just found low. If anyone can help, I appreciate the best I could find that you could self-short a single path and relate it to matching. Here, this would Choose another player. Not sure.
I think we found ourselves in a
Pickle.
yeah. Oh. Yeah, that's what dynamic programming is.
Okay, node only. Max path through left child plus node plus right. Max path from left child plus node plus. Okay.
Anyone in the chat have any insights on this?
Node only. Max path through left child
This
plus
is
node.
problem
Wait,
124.
go back up.
Sorry.
Wait a minute. Wait a minute. That's that could work. That could work. That could work. That could work. Yep. Yeah, that could work. Yes. And it's not that bad. Because what we're trying to do, right? The only problem I was having with this is that for every node, we have to start a new count, right? Because every node has its own little edges or own little neighbors, right? For example, if we go to Excalidraw, right? Go here, right? This one has this 2 and this 4.
Yeah.
Wait, no. Yes, this 4, right? Because it's connected to each path.
Or it
Yada
could have
yada.
a 5.
Or it could have a 5 too, right? This 2 has another path of its own with its own number, with its own maximum number, right?
Yeah.
Right. So here, what's basically says like, all right, go 1, right? It goes here. So this is gonna be right plus 1 plus 1, whatever right is, right? Over here is gonna go left plus 1, or it could be right plus left plus 1, right? Right? So it could be either the right subtree, the left side, or both of them combined, right? Which includes this, a path from here to here and here, right? Or from here, here, something like that, right? 2 is the same thing, but 2, it's going to be the node itself, right? And we choose which one is the highest. Either this one, if this sum, or this sum, right sum.
Mm-hmm.
I don't know if that makes sense,
Mm-hmm.
right? But yeah, so like the professor was saying, we're going to get the maximum of the node of itself, because the node can also be, right? Could be also an option. The right plus node, left plus node, and gotta get the maximum of all those. And actually, this works because we're back into the fact that if we assume this, right, this works. That's recursion. You assume something, you assume the result is right, and the programming, is it? Let me check my notes. Let me see.
Note
I think it was the other. Note check. No, recursive thinking is we know how to solve the problem, so we know how to solve this. So we know the output, right? We know what we want. So we for sure know how to solve that. Dynamic program is we assume that that this works,
That
right?
works. Yep.
That works,
How are you gonna implement
and we get
the
here.
yeah?
Yeah,
How are we gonna do that?
yeah. Recursion is the other way around. We assume the output is correct, and we're just trying to solve this, but we assume the output is correct.
Oh, I see. Okay.
Yeah. But to be honest, I'm not sure if I'm still confused with the paths and stuff.
Could you explain a little bit more on what you mean by right plus one, left plus one?
Yeah. I mean, I'm still the idea for me is vague a little bit. So, but to my understanding, to my
Damn, it's
oh,
getting cold in my room.
last Christmas I gave you my heart and you gave it away. No, 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 no. Last Christmas I gave you my heart and you gave it away. No, 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 no,
I don't think
no.
that's how it goes.
I think that's how it goes.
No.
Oh, man. Last
Christmas, I
Christmas.
gave you my heart. The very next day, you gave
Oh
it
yeah,
away.
yeah. I think yeah, I think you're right. I think you're right. Somewhere. Sorry.
Okay, man.
Last Christmas, I gave you my heart. Yeah, but the very next day, you gave it away. You smart. You smart. Okay, so
Sometimes.
here, pretty much, you either the note the maximum,
Uh huh.
right? It's either the right path,
Uh
right?
huh.
The right subtree or the right path plus the node, right? Because we still have to include the node.
Yep.
And it's either the left plus the node, right? Or
Yep.
it's either right plus left plus the node.
So you're saying it's either
I think so. Not sure.
node plus the left.
hmm And you do this for every single node.
Okay. So it's either the node plus the left plus this or this, and you continue that. Or it's this plus the this or this, and you continue that down the line. Or it's just this.
Mhm.
These. Or what happens to if it's this plus this plus this?
Well, that's what I'm thinking because I don't think this is a full solution because, like you said, what if two or four? What if this is a negative, right? And I got this, right? And I'm saying, oh, right plus node. You get me? And since node is negative, it's gonna reduce the amount, the sum. So that's where it's not equal to greatest. Go back to the comment. Let me see. Let's read it again.
Read it again. Read it again. This is a comment.
I don't know. I don't know. Because that's including the one. Let's go to the example. Let's try it out.
Wait, Jose. 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 Wait, Jose.
Yo, yo, yo. What am I waiting for?
All right. All right. Hear me out. Hear me out. Maybe this is something you're already thinking. Okay. 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 Ready? 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 Hold up. Let me get a picture.
No, I don't agree
No,
with
no.
it.
I'm not gonna get a
No,
picture. Okay.
I
Ready?
don't
Ready?
agree with
Ready?
it.
So, I'm gonna delete my stuff. My stuff right here.
I don't agree with it.
Delete. Delete. Delete.
I
delete,
see a bug already. I see a
delete.
bug already.
Delete.
Yeah, yeah. I
I
see an
know you do. I
exception,
know you
bro. I
do.
see some memory
Okay.
leakage. You know,
Okay.
runtime at line
One,
24. On line 24, you're gonna get a
1, 2, 3, 4, 5, 6, 7. I guess. Boom, 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 boom. Okay. Ready? You're doing okay. I'm just throwing it out there. I'm just throwing it out there. I'm not saying it's perfect, right? You start off by doing this. Okay? You find the max. The max. Is it gonna be these two? Is it gonna be these two? Or is it gonna be the whole thing? Alright, 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 alright.
Mhm.
You find the max. If it's the whole thing, well, actually, no. You just find the max. Then you go to the left, and the same thing. So the max right here would be 4, 6,
P3. 6 will be R3.
6, and that would be all three. Okay. Now you're going to the next one. So now we move this over here. Then you're gonna say, is it gonna be this, this, or all of them?
All of
Right?
them.
All of them. Okay, that already ruins it. Okay, okay. Hold on. I guess that already ruins the thing because you can't split. You can't, the path can be this, and then goes both ways. So, but basically,
Yeah, I see what you're trying to do. And I think it
what I'm
works.
basically, it's like you do each one, but I guess maybe each one after this first one you do, you're only checking if it's the left or the right. Maybe. So maybe only after this first one, where you could actually check everything. You could check if it's all three. Once you're done with that one and you're into the subtrees, your only options would be either this or this. And you're still allowed to go over here with the same thing. It's either gonna be this or this. Because you could still path from here all the way up to here like that, or you could do over here all the way to here like that. So there's options there. You let me know what you think. What am I missing? What am I doing wrong? What am I not understanding? Something along the lines of that, where that's where you do it into each recursive.
You're onto something. You're onto something.
I'm onto something.
You're
I'm just
onto
throwing it.
something.
I'm throwing it to see if it sticks.
You're onto something. You're onto something. You're onto something. Yeah.
I'm onto
Yep.
something. I'm onto something.
You're onto something. You're onto something. You're onto something. But I'm not. I think it works. I think it can work. Yeah, for sure. But it still needs like a little bit more.
It needs a little bit more.
Mm-hmm. Yeah. Okay. So what I was thinking, right? For example, in
Alright.
this example, we were given.
Where are you at?
I'm trying to do this kind of job, but okay, right here. Below yours.
Okay.
Right. We're like this. We say
Okay.
it could either be the node, right? The node
Yep.
itself, right? The node, right? Boom. It could be -10,
Uh-huh.
right? That's the answer. Right. One of the answers. It could be.
Dude, that wouldn't work. It's because you're not starting from the top. You could do a path that's down here as well. Okay.
That's what I'm going. That's what
Okay.
I'm going.
Okay.
We're kind of gonna use your method, which is a little bit of extra.
Okay.
It could be the node. It could be the right. It could be the left. It could be the right plus node, right? And or it could be the left plus node, right? Or it could be node plus the children, right? Don't you worry, my guy. I got you. Node 10,
Yep.
right?
Yep.
We can store that
Negative
10.
10.
We'll go 10, right? We go to the right side.
Yep.
And we do it all over again, right? We go here, shoom. Node, it could be 20.
20.
It could be 20,
Okay.
right? We go to 15. We do the same thing, blah, blah. It's a 15, yo, whatever, right? So we got 20. We got 15. We got 17.
Uh-huh.
Right? We got 7.
7.
7. We got the right plus node, which is 35. Right? We got left plus node, which is 27. And we got 42. Right? Boom. We get the max. Wait. Let me think. Let me think a little bit.
Okay.
Let me think.
You're onto something.
Let me think. Let me think.
All right, man.
All good. It's because it does work, right? It does work.
Yep.
But because let's say we have another one over here, right? Boom.
No.
Right?
Mm-hmm.
Gonna go, and then 15 is gonna get its own number, right?
Yep.
Let's call it X. X is gonna return a 20. But 20, right? And 20 is gonna be like from 20, it's gonna equal all of this, right? This 20, right? X is gonna transfer X plus 20, or X is here. It's gonna turn here, right?
Yep.
And then we can either keep that right. Oh yeah, I think it works. Yes. Because my thing is like, oh well, this X plus 20 is gonna be affected by this -10. If it is a -10, then it's not an adjacent path, because 10 is not connected to 15 nor to any of its children. But we don't have to. -X plus 20 doesn't have to be affected by -10, because we got it right here, which is by itself, right? But what if it wasn't -10? It was plus 10, right? Now, if we're adding plus 10, this is going to be greater if we're going to choose this one right here. None of that makes sense.
No, I lost
because
you a little
it's
bit.
because 10, right? 10 is not adjacent to y and z over here, right? Because 10 is all the way on the top, 15 they it's not a direct edge, right? Of y and z.
Wait, you're being serious? That it
Yeah,
needs to be a direct edge?
it has to be a direct edge. So that's why this approach wouldn't work as much.
Wait, so at most it's only gonna be 3 nodes?
Yeah. Well, 4 nodes
How would it be 4?
because of 20. 20 is connected to 15.
Oh, okay. So if we okay, just let me just clear that up real quick. If if we're saying 20 is the mother node or whatever you want to call it, the main node.
Parent node. Yeah, yeah.
Well, not really parent. I'm just saying like the center of the adjacent nodes. Let's just say that.
Okay. Yeah.
At most, it can have 4 because it would be this. I did not.
Yeah.
It'll
Yep. Yep.
be
Yep. Yeah.
it'll be this. Oh.
I mean, you can use the laser.
Yeah, the laser.
Yeah, it
It'll
could be
be
this.
it'll
Yeah.
be this. It'll be that, right? It won't be this down here. Like it won't bring that down here.
No. Yeah,
Okay,
I don't
okay.
think so.
Okay.
Yeah. So that's why we have to preserve this value in here, right? In here, and check. Alrighty, is this value here bigger than my current maximum, right? So we can preserve it. So technically, it could be. Oh, it's because I have to add the. You got the right, the left, and the node. Not sure, homie. We were on to something.
We're on to something. We're on to something.
Yeah, because that's the thing. We have to prevent this from getting added to the x plus 20.
And then again, this happy music comes on again. Oh man. At the wrong time, this
Man.
happy music wants to show up all happy and oh yeah. No, it's not the mood right now. It's not the mood.
I mean, we got something going on. We got something going on.
I need to concentrate. I'm not trying to be all happy. Hmm. I'm still holding on to this right here.
Yeah.
I'm still holding on to this. This is great. I like this. It's just how will we throw it into this?
Yeah, because the thing is, it does work. Like it goes, give me the right, give me the left. I'm the node, right? I'm gonna choose the left and right. Which one is the greatest? But that doesn't. But we also have to include 20, right? But the right and left might not be a direct adjacent nodes of 20.
So wait. So what you're saying is, let me bring it back a little bit. Do you mind bringing back the other text you had right here? So you're saying, you're saying the options that we have. Can I delete this green right here?
Yeah.
Can I delete the X?
Yeah.
Okay. You're saying our per subtree, per node, I guess, per node. Our options are we have this, we have this and this, we have this and this, or we have this, and this. So we have node plus right child plus right child's children.
Mm-hmm.
At the very most, we have node plus left child, no, or if we want to just generalize it even more, node plus child's children. That's the very most we could have it, because that would still be adjacent based off
Mm-hmm.
this node connected. So those are our options, if I'm understanding correctly.
Mm-hmm.
Is we have node itself, we have node and left, node and right, or node and children and child's children, the grandchildren.
Mm-hmm.
But anything more than this, like if this has children down here, you can't do.
Yeah.
Okay. So the same thing you said. How about you just go to each node and get out of those 4 options, like you're saying, just calculate the 4 options, get the max, right? At the very least, let's just say, just store all the maxes. You store all the maxes, and somehow you store what nodes were within that max, and then boom, that's the path.
Well, the thing is,
optimize it even more, you have to figure out how to optimize it better. But at the very least, you do each node, you do whichever option was the greatest, and you store it. But what's the thing? What am I missing?
what is that? Alrighty, 15, right? Whatever. We do the math here. This is the maximum, right? Let's assume this is the maximum, right? If this 15 gets carried to 20, right?
Well, that's what I'm saying. You're thinking of it as, how are you gonna add it? Like, how are you gonna carry it?
Wait.
I'm waiting.
Let me see.
I'm paused. Also, we just got a new sub, by the way.
No way, really?
Yeah,
Hey.
it went up. Thank you very much, whoever it was. Appreciate the sub. We do this every week, 10 a.m.
Hey, bro, you down to do 20 more minutes?
Okay.
Yeah, because I'm starving over here. I don't know about you. I don't know how you're feeling.
Well, thankfully, I'm not feeling bad right now.
Really? Okay.
But hey, if you want to go 20 minutes, I'm down. Whatever you.
All right, bet. Let's do 3 hours. 3 hours for the 20 minutes. Alrighty.
So, I understand what you're saying.
Yeah, I know. I think I get you. I think so. Let's say we get the max of that, right? Let's say we get the max of 15, whatever, right? But here we're just it's because yes, 20 the grandchildren, right? This, right? But how are we gonna know what's the sum of 20, 15, and 7?
Well, that's what I'm saying, is the least optimal approach is that for every time you're at a new node, you do the calculation. You do the calculations for everything. So you're gonna say 10 plus its left. What is that? Or in this case, it'll be 1 or -1, right? And then you're gonna say -10, 20. That's gonna be 10, right? And then the other option is, okay, this plus the children of 20. So you say, okay, if this is 10, let's add 15, let's add 7. Or the other option would be this plus 20 plus this, or plus this. Which one's greater? So that's like the least optimal way, is that for every node, you're going to do all those calculations, and you're going to say, that that's the max of this node, the max options.
Mm-hmm.
So figuring out a way way to optimize that is the question. But I feel like that
Yeah,
is the
yeah,
starter. Is the starter.
yeah. I'm just thinking a little bit. Let's see. Um. Let's see. Hmm. Yeah, we'll have to use a bunch of variables. Hmm. Damn, this is a tough one. This is a hard one. For sure, for sure. Because I do get what you say, but I don't know. I feel like there's a way where you get. It's not. Wait,
How you do a J in cursive?
Yep, yep. Damn, bro. I don't know. Right now, my brain is fried, brother. Can't think.
Seriously, man. You
Huh?
need some coffee in your life.
I need some coffee. Dude, I have a coffee maker, but my brother forgot to remove like the filter with the coffee he used a couple months back. Tried using it, bro. The coffee had mold on it, dude. I was like, oh heck no.
Nothing wrong with a little bit of mold.
You think so?
No, I'm joking. I had similar thing. Oh, this is actually really bad. You know the coffee mug or whatever. Well, not the
Yeah.
mug, but the one that it dispenses the coffee in. A
Yeah,
little
yeah.
jug. I had a little bit of coffee there, like a maybe like an ounce of coffee. Maybe that's a little too much. Maybe like um, I had a little bit of coffee still remaining that I
Yeah,
didn't
yeah.
flush out, and I left that thing in the coffee machine, and I didn't wash it, and it was
Ooh,
there for
fast.
months, and like you said, there was a layer of mold at the top of
Yeah.
the liquid.
Damn,
All
bro.
I did was clean it and then used it.
I
Cause
guess I'll make myself some coffee right now.
so you haven't
Hopefully I
cleaned
don't
it.
die.
You haven't
Huh?
cleaned it. You
No,
haven't
I've
cleaned
cleaned
it.
it. I've cleaned it already.
Oh,
I've
okay.
cleaned it. Yeah, yeah, yeah. Now for
Yeah.
sure I saw the thing. I was like, heck.
I don't know, Jose. I think we're not there.
I like your approach. I like your approach. Oh man. Yeah, I think I'm gonna call it here, brother. Um
All right, man.
yeah, cause I was doing homework before this, so my head was already like used up a little bit, and then with this problem, oofas. So if you're okay with it, I'm okay with calling it here. What's your call?
Yeah, let's call it, man. I'm looking at what it shows right here. BFS. Optimal. Do you understand this?
Oh, let me see. Let me open up your stream. Let's see. Division. Okay. Oh, we have to. Oh no, do we have? No, we have to return the maximum. No. So
Yeah.
DFS. We go to the left. We go to the right, and then we go again. Left, 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 left. We go all the way left. Right. We go all the way to the left. We go all the way to the right. Yeah. Yes. So we go left. We go max left of 0. Point to max. What's left? Okay. 0, 0. Return 0. 0, 0, 0. Return 0. Respond to position 0. We go max. We go max. Root val plus left plus max. What? What?
Yeah, you're saying the root plus
Yeah,
the
yeah, but
max.
like,
Which one's?
but that's false. Or maybe I'm misunderstanding the path. Because if I'm misunderstanding what the path means, then that works. Because what this is doing is saying like getting the left deluxe max, adding it to myself, returning that to the parent, and I'll get the left and left of both, re- added to parent both parents, give it back, then add to the left, add to the right, add both parents. Huh. So it starts at the very bottom, it checks that, and then goes to the parent, checks both of them, and then it returns that to the other parent, checks that, and then returns that to the other parent, and then to the other parent. I don't know, dude. The definition of path is very.
I just want to see how it looked like in Java. Oh, not that bad. I want to see how it
So
looks
a
like in
path
C.
is a binary sequence of nodes where each pair of adjacent nodes. Oh, we've been reading it wrong. Okay, that makes sense. All right. A sequence of nodes where each pair of adjacent nodes is the sequence has an edge connecting them. So pretty much says if there's adjacent nodes, that's an edge. Pretty much a path that can start anywhere, a path that can start anywhere in the tree. From that node all the way to the leaf. Pretty
Okay.
much. That's what it's saying. What we were saying is that it has to be connected directly. What I was saying, right? So that makes it a lot easier. Okay, makes sense. Yeah, yep. Okay, yeah, that could be. Yeah, that makes a lot of sense. It was just understanding the problem.
All right. I guess we'll have to say that
Yeah,
for next time.
yeah. I mean, I can explain it real quick if you want.
No.
That way you can know. Okay, next time then.
I'm gonna watch the video right now once the stream ends.
Yeah.
Mm-hmm.
Okay, fair.
All right, Jose. What are some last
All right,
words,
my
man?
guy.
Last words.
Well, I apologize for cutting it short, but my head is fried right now. I think
Cutting
I'm
it
gonna take a nap
short.
right
It's
now.
almost 3 hours we've been
That
streaming.
is true. That is true. We've done 3 hours, so it's actually one of our lengthiest ones.
Yeah.
Compared to the previous ones, where we've only done like an hour 30, an hour.
Yeah.
Yeah. So, but no, guys, thank you guys for coming in. I know First Shield was here, Orcus was here, Nightbot was here. So thank you guys for coming in. Thank you for the person that subbed. Thank you. We're almost there to 500. We need 65 more subscribers. Share, likes, subscribe, whatever you guys need. Just go in there. Boom, boom, boom. And yeah, appreciate everything you guys for tuning in. What about you, Carlos? Any tips, tricks, advice?
Um, no, I think that's about it. Um, I think we learned a lot this one,
Yeah,
and we're excited to continue it next week.
yeah, yeah, yep, yep, yep. And
Yeah,
it's if you yeah. It's a good problem, but you have to really understand what a path means, what adjacent nodes mean to understand it. But
yeah.
it's a good problem. We'll figure it out. We'll figure it out. Yes, sir.
All
All
right.
right, my guy. So if I got nothing to say, if you got
No, I
nothing
think
to
that's it.
say,
I think that's
so
it.
thank you guys for coming in. Have a great day. Have a great morning, afternoon, evening, whatever it is in your time zone. Just have a great day and see you guys next week. Bye
All
bye.
right. See y'all.